Welcome back. Today's lesson is on composite functions. So far, we've been doing lots of merging of functions, whether we add or subtract them or multiply or divide them. And today we're going to stick them together in a completely different way. Composite function is going to be what happens when we put a function within a function and then see how those react. Now, the notation on this is a little bit new for most people anyway. Um, the idea is easier than most people make it out to be. What I want you to think of is any function f at x equals blah, blah, blah. The blah, blah, blah just tells you where to plug in the x. And when I say plug in x equals 3, people have no problem plugging in a 3 wherever the x was. Today, I want you to keep that in mind. Wherever you see the thing in the bracket, instead of x, it might be 3. Plug that in wherever you saw an x before. If it's not a 3 and something else, plug whatever it is in that spot. Let's go over and see what these actually look like by starting to look at rabbits and wolves. So we know that in nature, rabbit and wolf populations are actually really closely tied to each other, at least in this hypothetical made up fake math world. In real parks, it is kind of true. There was a thing years ago, actually a study in Yellowstone National Park where they killed off a bunch of wolves to try and make the park safer. And people thought, okay, well, what happens if all the wolves die? And the one thing that they never considered was the soil erosion. They had complete erosion of soil around the rivers, and they couldn't figure out why. And it was because the wolves were eating the herbivores, the things like rabbits, and the rabbits, when there was no wolf there, grew in population and ate all of the plants along the riverbeds and caused massive soil erosion. So that's the kind of crappy unforeseen stuff that can happen. But anyway, going back to our math problem, today we're going to look at these wolf and rabbit populations and how they relate to each other. The first thing we'll look at is the rabbit populations, which we'll call R at t, number of rabbits at time t, where t is in years, and it's modeled by this function, R at t equals 50 cos 2 pi over 6t plus 100. So hopefully it wasn't that long ago that we covered trig functions. You remember a little bit about how to do them. And I'm going to make the rabbits, they're herbivores, so I'm going to make them green. We'll draw their graph. Okay, so the cos function we know starts off at its high value and then goes to its low. Our starting point, our midpoint is going to be 100. That's the plus 100 at the end. However, from there, we're going to go up and down 50 because that's the amplitude of our particular cos function. So that means that we're going to start off at a height of 150. And I'm trying to keep the graph on the screen, the whole graph on the screen along with the equation. Inside the cos, we have 2 pi over 6t. And what that means is that this is going to repeat the pattern every 6 units. So in this case, every 6 years. So that means that after 6 years, it'll be back up to that point again. Now, halfway between those two times, which will be at 3 years, we should hit our minimum, which is going to be 100 minus 50, which is just 50. And I'm not going to worry too much about the details of making this graph perfect. We've got the right amplitude. We've got the right shift up and down. We've got the right period. I'm just going to kind of draw them so it looks kind of like this. It should go through 100 at about 3/4 and, or I should say 1.5 and 4.5, I think. And then it's going to do the same thing again. So over the 12 years we have here, it's going to go through 2 complete cycles. Okay, so there's our rabbit population. The number of wolves, W, is in the same reserve, can be modeled by the function W at t equals 0.t R at t minus 2. Let's just stop and think about what that means, because that's a function within a function. So W at t equals 0.2. Okay, right off the bat, 0.2 times the number of rabbits just means there's going to be one wolf for every 5 rabbits, but not at a given time. It's actually going to be at the rabbits shifted over to. Okay, now we got to make sure that we get this part correct. Which direction do we have to shift? So here's what I want you to think about. Whatever the rabbits are doing at time 2, or sorry, at time 0, the wolves will be doing at time 2, because when I plug 2 in there, I get 2 minus 2 is 0. So R at 0. So whatever R is doing at 0, the wolves do at 2. So that means they're going to be shifted over 2 to the right 2 years later, and they're going to have a smaller amplitude because of the 0.2 in front. So that means it's going to go 100 plus and minus 10. So now we get our peak at 2 years, and it'll be 100 plus 10. And then that repeats, that repeats every 3 years. So every 6 years. So 2 to 8. And halfway between at 5 years, it'll be 100 minus 10. And then we go through our midpoint somewhere around there. And then that repeats. And of course, you don't have to take my word for any of this, because you can graph it in Desmos if you'd like. Now, some of you may be wondering, well, why is it at t minus 2? What's the relevance of that? Well, think about it this way. If you're one of the wolves and you say, hey, it's a great summer, there's a lot of rabbits out there. So you go out and eat a bunch of the rabbits. The rabbit population is going to drop because you're eating them all, and your population is going to go up because you got lots of food. So what will happen next year is there's going to be more wolves but less rabbits. And that means that the food will be less plentiful. So then the wolf population will drop because there's less food. And because there's less wolves, the rabbit population will go up. And I'm saying every year, but it's actually more like every 3 years. So there's going to be a slight delay because it's not until a while after the rabbits start to go down that the wolves will start to go down. When the rabbits are the highest, the wolves were definitely going to go up, and vice versa. And this is pretty typical among animal populations. Of course, real animal populations are more complicated than this, but the idea is actually pretty firm. Okay, I'm going to point out here, and I've mentioned this I think a few times in the course, just for interest's sake, and that's that we should really write our equation w at t as w at t comma r, because we have absolutely no way of solving or looking at wt here without knowing what r is. So w is really a function of r. That is kind of important. It doesn't really affect any of our math, but just it's a better way to write it. And very few textbooks do it, by the way. Okay, so let's find a population for w of t, like actual w of t that only involves time, that doesn't require an equation for r at t. So here's what we're going to do. We have w at t equals 0.2 r at t minus 2. So what that says is take our equation for r at t. I'm going to go back up for just a second. And our equation for r at t was 500 cos 2 pi over 6t plus 100. Or sorry, 50 cos. 50 cos 2 pi over 6 t, leaving that out for just a second, t plus 100. Oh, and I realize I just messed up my graph, but we'll fix that in a moment. We will fix that in a moment. Okay. Here where we had the t before, we no longer have a t, we have a t minus 2. So that's all it's saying is replace t with t minus 2. All right, can I make this a little bit prettier? A little bit. So 0.2 times 50 is 10 cos 2 pi over 6 t minus 2 plus 0.2 times 100 is 20. All right, now we've expressed the population of wolves as a function of t and no other variable. So we no longer need to know anything about the rabbits to find out the wolf population. And we did that by plugging in the rabbit population function into W and T. Okay, this is where I just realized I made a little bit of mistake on my graph. On my graph, I did the red wolf population up and down from 100, but it's actually supposed to be 0.2 times that, so it should actually be up and down from 20, not 100. So everything's just going to be shifted down a little wee bit. My apologies. But at this point, I'm not redoing it. So same shape. It just is going up and down from 20 since it's 1/5 of the rabbit population. Now can I erase this without really screwing things up? I think I can. I know you guys are all mad at me because I have a nice way to erase and you don't, but them's is the breaks. Okay, so that wasn't too bad. We just plugged in r at t wherever we saw r at t in the function. Now we're going to use something called fog notation. And it's called fog notation because of the way it's written. Technically, we're not writing the word fog, we're writing f composite g, which is just often called fog of x, f at g at x. And I do want to point out that despite this new notation, we can actually write it as f at g at x. The one on the right is the one I find students like more. It's a little bit more easy to understand, but both of them are acceptable and you have to be able to read and deal with both. Okay, so let's start off with just how this works. We have two functions here. F at g is x squared, or sorry, f at x is x squared. G at x is x plus 3. So just two simple functions, one quadratic and one linear. So normally I wouldn't bother starting with f at x because it doesn't matter. Well, better yet, what if I wrote f at a? If I wrote f at a, most people right off the bat would say, well, that's just equal to a squared. And the reason for that is whatever you plug in here, you plug in there. I mean, that's what the original equation says. You plug x in here and then square it. So really what that says is that f at g at x is equal to g at x squared. So instead of plugging in a number for x or a letter for x or anything else, I'm plugging in a function for x. And then g at x squared is x plus 3 squared, which, you know what, we're going to graph it, so why don't we actually just leave it in that form? I was going to say expand and collect like terms, but for graphing, it's actually a little bit nicer to do it that way because that one is just a parabola shifted 3 to the left. So now that we've got that, a parabola shifted 3 to the left, I think looks like this. And by the way, I'm not going to spend too much time on these graphs. They're not that important. Okay, the second one, gof of x, or g at f of x. Again, if you'd like to write it that way, you could write it as g at f at x. And what that's saying is g at x, which would normally be x plus 3, I'm not plugging x in anymore, I'm plugging in f at x. So that becomes x squared plus 3. So g at f at x is just a parabola shifted upwards 3. And of course, these can become much more complex than this, but these ones are pretty nice. All right, well, what about f at x? F at x, well, f at anything is that thing squared. So now it's f at x that we're squaring. And since f at x is x squared, it's just x squared squared. So another way to think about this is f at x and g at x are functions. They're basically just an instruction about what to do with the input. If I plug in a 5, it tells me, hey, take the 5 and square it, or take the 5 and add 3. So now it's saying, take the x squared and square it, or whatever. It's just the instruction going through twice. That becomes x to the fourth. And x to the fourth is a quartic, so it's going to have a 0, 0 there. When x is 1 or negative 1, y is 1. When x is 2, y is already way off the graph at 16. So it's going to go up really sharp. And just a reminder that near 0, higher powers of x are going to be much flatter than a parabola normally would be. So it's going to be something like that. All right, a couple more. G at x. Again, that could be written as g at x, which I find most people have an easier time understanding. And g at x is x plus 3. So now instead of being x plus 3, it's g at x plus 3, since that's literally what I'm plugging in. And that's just x plus 3, which is x plus 6. And this is going to be super easy to graph because it's a parabola moved up 6. So it goes like this because there's no room left on the graph. But yeah, it does something like that if we kept going. Okay. G negative 1 of g at x. I'm going to remind you of something just for a second over the side here. If we wanted to solve sine x equals a half, what we would do is type a half into our calculator and do sine inverse or sine negative 1 of x. And what we're doing on the other side is sine negative 1 of sine x. And then we're getting some value out. This side is just x, and this side is a number. In fact, in this case, I think it's pi over 4. Sorry, sine of 1/2 is at 30 degrees? Yeah, 30 degrees, or pi over 6. That's it. But the point is, when you do the sine negative 1 of sine x, you actually just get x back. So I'm going to suggest that that actually is what we should get here. But of course, let's not make it that simple. Let's just take a moment and think about how this is going to work. So g at x equals x plus 3. So I'm going to write that as y equals x plus 3. And that's for g. G to the negative 1. Remember, to do a inverse function, all I have to do is reverse x and y. And now I can rearrange that for y and get y equals x minus 3. Okay, so what that really means is g to the negative 1 at x equals x minus 3. The instruction G says take your number, add 3 to it. The inverse function, how to undo that, it says, okay, take the result, subtract 3 from it, and you're back to where you started. So then this becomes G negative 1 of G at X equals G negative 1 of X plus 3. And the instruction here is X minus 3, but we're not plugging in X, we're plugging in X plus 3. And X plus 3 minus 3 is X. And sure enough, we're back to where we started. So G negative 1 of G at X is just going to be X. And that's true for any function. Any function and its inverse. The inverse function will always take you back to your starting point. G is the instruction to move forward. G inverse is the instruction to move backwards. So here we did something to X and then we undid something to the X. And so we're back to X. I realize that's confusing. I hope I didn't lose too many people there. Please check your ears for bleeding. And if you're all good, move on. If your ears really are bleeding right now, just maybe stop and take a break, possibly a doctor. Question 5. We have a couple of functions there. U at x equals x squared plus 3x plus 2, and w at x equals 1 over x minus 1. So the first thing we're going to do is evaluate u at w at 2. Now there's a couple ways you could do this one. You could actually work out w at 2 first, which is what I would do. W at 2 is just 1 over 2 minus 1 is 1 over 1, which is 1. So then this is just equal to u at 1. And now I plug in 1 and I get 1 squared plus 3 times 1 plus 2. And that's just going to be 3, 4, 5, 6. Okay, so that wasn't that painful, hopefully. This one here is w at u at negative 3, if you prefer to write it that way. And again, over here, I'm just going to put u at negative 3 is equal to 1 over negative 3 minus 1, which is negative 1/4. Now that I have that, this is the same thing as w at negative 1/4, which is going to be 1/4 squared plus 3 times 1/4 plus 2, which is 1/16 plus 3/4 plus 2. And at that point, I think you can basically find a common denominator, which will be 16, and it'll be 1/16 plus 12/16 plus 32/16, 32, 33, 43, 44, 45/16. And I unfortunately don't think that that gets any prettier. 45 is not divisible by 2, and 16 is only divisible by things that are even. So I think we're stuck. But that's basically how these work. Plug one thing in, then plug in the other. One last little question, word problem to finish off the lesson for today. And we have a music store that traditionally made a profit from sales of CDs and cassette tapes. I'm actually basing this on it's a real CD store that sells used CDs and did at one point sell used cassettes. Now they've moved into things like video games and Blu-rays and some other stuff, but they are a real store and they are local. I won't say which one it is, but some of you probably know who this used CD store is, used DVD store is. But when they started, they made their sales on CDs and cassette tapes. The number of CDs sold yearly in thousands as a function of time t in years. Since the store opened can be modeled by the function c at t equals negative 0.03 t squared plus 0.5 t plus 3. And the number of cassette tapes sold, t in thousands, as a function of time can be modeled by the function t at t equals 1.5 minus 0.1 t. And you can see that the number of tapes sold is definitely dropping each year. The store opened in 2000. That part is a lie, but for our math, let's just do that. At which point t equals 0. Little t equals 0. So graph both functions up to the year 2018. Okay, our first one. You know what? Actually, just for the sake of time, let's not graph these by hand because it's a pain in the butt, especially since C at T is not in a nice format. And let's just go over and do that in Desmos. Okay, so we have our number of CDs at time t is equal to negative 0.03 t squared plus 0.5 t plus 3. Now this is number of CDs sold in thousands, not just number of CDs sold, which would be really sad. And we wanted to go between 0 and 18, so actually that's about right. And the number of tapes sold at time t is equal to 1.5 minus 0.1 t. And I was going to say that this function, well, the number of tapes sold in real life these days is extremely low. This function may not have to be in thousands. It may actually be the number of tapes actually sold in Kitchener. 1.5 a year, that's about it. Okay, so those are our two functions. The store sells CDs for $3 each and tapes for $2 each. The total revenue R from the sale of CDs and cassette tapes can be modeled by the composite function R at TCT. You know what, I'm going to go back over to this since I'm reading that question anyway. The total revenue R from the sales of CDs and cassette tapes can be modeled by the composite function R at TCT, because I have to know the time, the cassette relationship, and the the CD relationship and the tape relationship in order to actually use that function. We want to develop an algebraic and a geographical model for the store's revenue and interpret the trend. Okay, first of all, I'm going to just, for interest's sake, or not interest's sake, but interpretation's sake, ask you why you think the 3 and the 2 are there. Give you a second to think about that. And what that's really telling me is that I'm making $3 per, or in this case, $300 or $3,000 per 1,000 CDs sold and $2,000 per 1,000 CDs or 1,000 tapes sold. Okay, and as far as this goes, that's going to account for inflation. So it's going up. So now we have a model which is quadratic and another model which is linear along into a model that overall is exponential. There's a lot going on there. So let's start off by just figuring this out. R at TCT. And again, if you don't like this 3 variable notation, you can put down R at T because it's going to be R at T in a moment, is equal to 3 times C at T. But C at T is negative 0.03 T squared plus 0.5 T plus 3. And plus 2 times the tapes, which is 1.5 minus 0.1 T, and then times 1.04 to the exponent T. And from there, we can do a little bit of collecting like terms and see what happens. So that'll be negative 0.09 t squared plus 1.5 t plus 9. Oh, I should use round brackets in the right places here. Plus 3 minus 0.2t times 1.04 to the t. And then we can collect some like terms here. Negative 0.09 t squared, 1.5 t minus 0.2 t is going to be plus 1.3 t, and 9 plus 3 is 12. So now I can say that that is R at t because it truly is a function of only time. I don't need to know anything about their CD sales or their tape sales. I mean, I did to derive the equation, but once I have it, if I was just given that, I could predict what their revenue would be without really understanding how many CDs they're selling or how many tapes they're selling. I'm feeling like I need to, like I'm getting to that age where I have to explain what a tape even is. I'm hoping everyone knows what I mean by tape. Like cassette tape? Yes? No? If you don't know, Google it. I'm getting old. Okay, so I'm going to go back over to Desmos. And I'm going to go back over to Desmos. And I could actually type in the model that we just got, and I will in a moment. But what I'm going to do first is actually just type in the original relationship. And even Desmos will accept the fact that I'm plugging in t, or just t. We're told that it was 3 times c at t. Can't type today. Plus 2 times t at t times 1.04 to the exponent t. So we get something that looks like that. And just a reminder, when we look at this, we're looking at a revenue of 23.7. Remember that this is for thousands of CDs and thousands of tapes, so it's going to be thousands of dollars, $23,000, not $23. And I can also actually plot it using, hopefully, my new function that works, which is just really a function of t. By the way, I'm not going to use that multivariate variable thing here for the TCR part up here, or TCT. It's going to confuse Desmos. Confuses you guys enough. But I'm going to put in negative 0.09 t squared plus 1.3 t plus 12 times 1.04 to the t. And yeah, so whether I do it this version, the blue one, which is using c at t and t at t, or whether I use the green one, which eliminates that and just uses the time, I get the same function. Okay, so what this is unfortunately saying, especially since I just set this question up, I chose the starting year to be 2000 just to make it sound new. Obviously, the fact that it has tapes in it does not. But it says that their revenue is going to go up from year 0 up to about year 10 and a half. So that would have been 2010. And then their revenue would drop. Ooh, this is unfortunate. Their revenue drops to 0 about a year ago. And that may have actually happened if this store that I'm thinking of had continued to do just CDs and tapes However, they were smart enough to pivot and change with the times, and that's why they sell video games and DVD movies now. But yeah, this prediction would be kind of grim for them going out of business about a year ago. Okay. That said, there is a problem with this model, and we could address it if we want to look at it carefully, and that's that it does predict that tape sales will go negative in the year 2015, which of course is not true. So what we could do to make this model slightly better, and mathematically it's very difficult to do, but at Desmos we can fake it. I'm going to put a restriction on the number of tapes sold and say that it's X is less than or equal to 15, because I think that's when it went to 0. Oh, sorry, T is less than or equal to 15. Less than or equal to. Okay, so yeah, that was where they hit 0 tapes. So what this is now taking into account, at least our blue model. Oh. Yeah, I'd have to put a conditional something on this. So Desmos is saying that whenever T doesn't exist, it's not getting an R, which it should. It should just assume T is nothing and C is whatever it is. So I'd have to fake that graph. Let me see if I can fake what it would really look like if we ignored tape sales. I'm going to do it in blue so it looks like a continuation of my other graph. Come on, blue. Come on, blue. Okay. I'm going to do that for T greater than 15. Oh, I'm going to have to change the variable on that. I'll call it D. Oh, that's not even the one I want. I want tapes to go away. Ah, dumb tapes. That's why no one wants them anymore. I don't know. N for no tapes. Yeah, I'm giving up on this one. It's not wanting to connect right. But either way, if tapes could go negative, that model seems to work just fine. Of course, tapes can't go negative, but luckily it's a pretty small negative number. So take that restriction off. So it won't affect revenue too much. Anyway, there we went. We took two functions, C at T and T at T, and plugged them into R at T and did a composite of multiple functions with multivariables and got out some semi-interesting results. So we shall stop there. Oh, develop. Yeah, we did that. We developed it and we talked about the trends. I think we've answered that question as much as we're going to. So I'm going to stop there. You can try some questions where we do composite stuff. I will point out that if you want to use Desmos to solve some of this stuff, instead of saying y equals, y equals, y equals, call your different functions different things like we just did with C at T and T at T and R at T. And that way you can actually type in the relationship between them. So you can do things like R at T equals something C at T plus something T at T. Anyway, yeah, if you do that with all y's, it'll graph them all individually, but you can't put them together as nicely. So give those a shot. Let me know if you're struggling, and I will try to help you. Otherwise, I will see you in tomorrow's lesson.